All right. I love this diagram. I don't know if it's the colors or what. It's just very grade schooly, primary, early 80s, comfy feeling. When they first introduced layers of the Earth to you guys, crust, mantle, core. At some point, they did crust, mantle, core, inner core and outer core. Well, no, I don't recall inner core and outer core in the 80s. I'm sure they knew about it, but whether or not it made it to the textbooks from the late 60s that we had. Yeah, that's no. I mean, they've always known about it, but I think it didn't make it into the textbooks. I also think the scale's off a little bit on this one. I don't picture the outer core being that thick. I haven't actually Googled thickness of the outer core compared to the thickness of the inner core. But nonetheless, it stands as a good diagram. You are in college now, so we have to go beyond crust, mantle, core, and even crust, mantle, core. And we're going to add, apparently not yet. We're going to add a couple more terms to that. Let's talk about the crust, though, real quick. You guys haven't had igneous rocks yet. You will be soon. This word basalt is an igneous rock. That word granite, everyone knows granite, is also an igneous rock. And what we're telling you is that the crust is primarily made out of two different types of rock. Oceanic crust is made out of basalt, and the continental crust is made out of granite. Now, hopefully you're thinking to yourself, wait a minute. He's been talking about limestone is everywhere. I know I've looked, I've seen sandstone, I've seen shale. Isn't that the crust of the earth? Yeah, but. All right. What we're talking about here is the original stuff deep down, not all the riffraff that's built up on top of it over the last 4.5 billion years. Okay? Picture an eggshell that's been decorated. The shell itself, the solid crust underneath, is the basalt or the granite. And there are parts where that still comes through. Okay, don't get me wrong. But we hardly ever see this crusty crust stuff. Even in the oceans, anywhere likely that you're going to be, if you could even get to the ocean floor, is going to be covered in sediment. All right? But you go out farthest to the deepest parts of the ocean, you should be able to see that basalt. Granite, again, you've got so much sedimentary rock on top of it, very unlikely to see it, unless you get to a point where mountain building has occurred and there's all this crumbling, and that crumbling made the sedimentary rock much easier to wear away. There's some pretty weird rocks exposed up in the Adirondacks here that really aren't at the surface anywhere else because they're deep crust, if not mantle, rocks. And it's the crumbling and crushing from the mountains that allowed all that to break off and sort of fritter away over the years. The mantle. We talk about the mantle as being molten. All right? And we say it's molten because when a volcano happens, we know that it leaks out and, gosh golly, look at that lava. All right, it flows all out. It's molten. It's melted. It's melted rock. Everybody knows that. Well, yeah, but what we forget about is the effects of pressure. on stuff. All right. The easiest way for me to explain pressure to you, we're not exactly in the right season now, but next time you're at Targets or Walmarts or something similar, you know those little green cans of propane that they sell for the tiny gas grills? All right. Next time you walk by one of those, shake it. Don't worry, it won't blow up. Shake it. Some of you may have already shaken one. What does it sound like is inside of it? Who said over here something? Liquid. Soda. All right. Liquid. Yeah, it's liquid. Have you ever lit a gas grill? Wait, and I just called it a gas grill, didn't I? Well, how does that work? If you turn that bottle on and a little water trickles out or a little gas trickles out? No, what comes out? It goes tss, right? A gas is coming out. You're like, well, I just shook it. It's a liquid. It's a gas. What is it? There's your chemistry, okay? When you pressurize these things, if you pressurize a gas, it turns into a liquid. So it is a liquid inside of the jar, but when you take the pressure away from it, it turns into a gas. I'm oversimplifying things, believe me, but that's the gist of it. So imagine if you have a liquid that you pressurize. It doesn't exactly turn into a solid, but it turns into a much different kind of liquid. They now use the horribly scientific word silly putty for a good reason. This is something that has actually modified in the time I've been teaching. We used to say Play-Doh. The idea is we want something that's malleable, okay, but they've added, the big difference between silly putty and Play-Doh is that silly putty is elastic. It stretches and goes back, or at least it has some bit of stretchiness to it. Play-Doh, on the other hand, is just squishy. It doesn't retract or anything like that. So they've added this elasticity to it, and it's a property that I guess we could use the word discovered, that they've discovered that it has in the last handful of decades. Or again, there was just a lag by the time stuff takes to get to the textbooks, which is more likely. But nonetheless, we don't want you to think that, like that propane bottle that you're shaking, okay, there's just magma sloshing around inside the earth. All right, it's much more like we've got this solid crust, then there's this really thick goo that it's sitting on top of. But it does still behave fluidly, all right? If you had Earth Science in high school, you might remember them talking about the convection cells and the moving of the material within the mantle. It flows, okay? But probably more information than you needed. But there are 3 parts to the mantle, all right? We don't really talk about them, especially the lower mantle. We've got 0 purpose for in this class. The word upper mantle does come up, but mostly we'll just refer to the mantle in here. The core. The core is iron and nickel, all right? And picture a giant ball of iron in the center of the earth. Maybe I should add diameters to these. Whenever I put numbers down, you guys always get worried that you have to memorize them. So I try to lean away from it, but I suppose it might be kind of helpful for relevance. So we have this solid inner core, and around that we've got this molten, essentially the same composition material. And we've already implied to you that this is rather important. As the Earth spins, this material spins as well, and it allows for an energy field to be generated. And if that were ever to stop, at least as we understand it, that would not be good. we just witnessed a Hollywood movie coming to fruition the other day with something launched from Earth, intercepting a satellite and, I'm sorry, not a satellite, an asteroid, and knocking it off course. They sent Bruce Willis up in the early 90s to do that in Hollywood. But at that point, I think they actually blew it up. That's a bad idea because that just makes a bunch of smaller asteroids. But it's still better than getting hit by one giant one, I suppose. There was another movie that, maybe this one had Bruce Willis, maybe the other one was Ben Affleck, but where the center of the Earth's core, the rotation was slowing down. And the magnetic field was slowly fading away, and they were suffering from all the effects of that one. That one's called The Core. I think the other one was Armageddon, or something like that. But every so often, Hollywood attempts to do geology. It's really interesting. So this is another one. And again, as I started to say, if the core, for whatever reason, started to cool off, which it shouldn't do for a very long time, eventually the radioactive decay will slow down. That will cool temperatures. That will change things for sure. But it's, again, nothing we need to worry about in the near future. All right, I told you, I started to tell you a couple minutes ago, well, we're in college now. We're no longer going to have crust, mantle, core. We need to add two more words, and they are lithosphere and asthenosphere. Just like we had that wonderful consonant cluster of sp in sphalerite in lab, we now have astheno in lecture. So the lithosphere and the asthenosphere. Again, I'm not concerned with thicknesses for testing purposes. The lithosphere is the crust and just a wee bit of the mantle. Imagine cracking an egg and there's always that little bit of egg you can't get off of the shell. You're trying to shake it into the bowl there, or at least not get it all over your hand or the counter and everything. Okay, there's a little more than that, but that's a wonderful visualization there. And then the asthenosphere is a bit of the mantle below that. It's important that it's not the entire mantle. We could use the word middle mantle here if you'd like. Remember we mentioned a slide or two back that the mantle is essentially in three sections, okay? So this asthenosphere, we're gonna loosely associate it with the middle mantle. And the asthenosphere is rather important, at least for now, because they think that's where the engine, the motor, the motivation for plate tectonics is happening. All right. They'll call it mantle convection theory, but when you actually read about it, you'll see that it appears to be these currents generated in the middle mantle that are primarily responsible for moving these lithospheric plates around. Again, remember plate tectonics. You may have heard that the crust of the Earth is broken into plates. True, but there's that goo stuck to the bottom. So technically now, it's lithospheric plates. What did you guys hear in Earth Science? Do they say lithosphere and stuff, or what they do? Yeah? Okay. I know that was like freshman year, a long time ago, but again, we'll have a whole chapter on plate tectonics. I introduce a little bit of it here just in case we don't get there. Sometimes, depending on the semester, how much I babble through this chapter, we just don't get all the way through everything at the end. So we're covering it here just in case. So unlike that nice, simple, happy little diagram we saw a few slides back, this is something more like what you're going to see on the test. I have this a line down the middle to help you keep things separate. We have the old school, we'll call it the simplified version, crust, mantle, core on the right. Which letter represents the mantle? C, good. Crust? D, good. Inner core? E, outer core? A, B, good. All right, you guys all see how that meshes up to more or less this previous slide. So we move over to this side, and we're introducing the terms lithosphere and asthenosphere now. Which of these would represent the lithosphere? A, exactly. All right. And then the asthenosphere is B. And I suppose I could have made the asthenosphere a little thicker, but that's how I drew it whenever I made this lovely picture. So crust, mantle, core, lithosphere, asthenosphere. Literally 2, 4, 6, 6 points on the next test, okay? So that's an easy sixer, hopefully, for you guys. But again, I found myself putting the final together and realizing that, oh my God, we actually didn't talk about this. So why we're getting it now. I mentioned we'd touch on plate tectonics just a little bit, and I kind of already did. There's not a whole lot more to tell you without getting really involved. I had Earth and Physical Science as a freshman, like many of you did, which would have put that about 84 or so. And again, the old joke about textbooks lagging, it was true. I'd say our textbooks were easily from sometime in the 70s. I learned about Continental Drift. All right. Plate tectonics has been around since the 60s. But it takes a while for stuff to filter, information to filter in. Continental Drift itself wasn't that old, in like 1911 or so. Alfred Wegener. And you've heard the story, I'm sure. He's looking at the map of the Earth and says, wow, these really looks like these continents fit together like puzzle pieces. Picture wooden block puzzles for kids. And he had all these great ideas. He even had some data. When you put it back together, you get the same types of rocks. East coast of South America and the west coast of Africa are a great example. You put those two little pockets right back together, and oh my God, literally the rocks just line up. Okay, we've got now computers and stuff. We could do this a whole lot easier. But he figured this out 100 years ago. You get the same fossils. Fossils are typically animals and plants. Obviously, those are products of environments. Arguably, you have one kind of environment over here in South America, a different kind of environment now in Africa. But when you put them back together, not only the rocks, but the fossils inside of those rocks match up, which means that they were alive at the same time doing the same thing in the same environment. I mean, he had just tons of data. Unfortunately, he had the unluckiness to present this to a bunch of geophysicists, as I understand it. And they're like, yeah, Al, this is great, but how the hell is it happening? Where's your mechanism? What, these things are just, these continents are just floating around on the ocean? They're drifting through the ocean? I'm making this conversation up, but you get where we're going. Okay. He's like, I don't know, but I know it's there. I know it happened. It didn't go over very well. It didn't exactly get forgotten about, but it didn't go anywhere. Till the 50s, 60s, when we started exploring, we got these cool little yellow submarines and started going farther and deeper and longer into the oceans than we ever had been. And we started finding these giant seams down there on the ocean floor, where it looks like crust was being made at some points and crust was being destroyed in other points. And they realized that it was just big conveyor belts. That's about when it turned over to plate tectonics. They said Al was right. Someone remembered his work. And they said, holy cow, he was right. If you move these backwards, you couldn't get this. Some of it still is bizarre. Like India, that's up attached to Asia now, used to be down where Madagascar and Africa, okay, plugs in right there. That's some hard explaining. But so many of the other pieces just fit together so easily that we can worry about that later, so to speak. Plate tectonics is, okay, you don't even find in these very strict religious groups where they complain about evolution and this, that, and the other thing. I don't even think they have a problem with plate tectonics. You can't. We have GPS units now. We know not only that these things are moving, we know how fast they're moving and in what direction they're moving. And by the way, he was right about directions too. And the reason that's important is because we still don't really know how it's happening. That's the thing. I explained this mantle convection theory to you. That's the working model right now. Okay. This magma that we were just talking about gets heated up close to the Earth's core. In that middle mantle there, it rises up, cools off, sinks back down. Lava lamp. Okay. Basically a lava lamp. And it sinks back up, gets heated up, rises again, and it makes these little convection cells, wheels. And those little wheels move the plates that are floating on top of them. Kind of like a current in a pond in spring when the ice is starting to break up. They think that's what's going on. But even that, North America is moving a different direction than the Pacific plate. Why would these little convection cells from the middle of the Atlantic Ocean all the way over to the west coast move westerly, westerly, and then once you get to the Pacific Ocean plate, that one's moving northwesterly. So what changes the direction of those things? They don't know. What drives those things? They don't know. Is it deeper than... So there's still a whole lot of unknowns, but it is unquestionable that it's happening. So they can now actually focus the science on the why. They don't have to just believe Al Wegener anymore. So, neat little history. Again, science sort of in action. Technology helping science come again. Age-old story and an ongoing story. So, and believe it or not, yes, there is way more to plate tectonics than that. There's a whole chapter on it. You get to learn about all the different boundaries and everything. But for right now, that's enough to get you through. All right, we told you this more or less. The lithosphere is broken into pieces, which we call plates. It's not just the crust anymore, not crustal plates. Technically, they're lithospheric plates. I still slip up and say crustal every so often, though. These lithospheric plates rest on the asthenosphere. And like I said, those currents within the asthenosphere float the plates around like ducks on a pond. And you may have heard the word, or will hear the word, plate boundary. That's just when one plate ends and another begins. It's the boundary. A seam. I use the word seam a lot. Any questions about plate tectonics? Layers of the earth, etc. Accelerate. Because I do believe that will end the conversation here. Here's a map The plates, generally speaking, they recognize 7 large plates. They more or less are your continents. The exception being the Pacific Plate, which is mostly ocean. This giant boundary between North America and Europe. We'll talk much more about that. It's a really tall mountain range. Biggest and tallest mountain range on the planet. This way, to the left of it is moving this way. To the right of it is moving this way. Technically, every moment of every day, North America and Europe are getting farther and farther apart. Don't tell the plane companies, they'll start charging us more. But it is getting bigger every day. This one right here, Pacific Plate boundary and the North American Plate boundary, is famous because that's where San Francisco and their earthquakes are. It's also responsible for our volcanoes, which you'll learn about in a couple weeks. If you skip to the other side of here, this is still the Pacific Plate. It wraps around. Where the Pacific Plate joins the Eurasian Plate, it's just a wreck over there. Japan, China, all those small little islands over there. And you see there's another plate wrapping around here. There's always, unfortunately, something going on over there. Lots of earthquakes. Not a whole lot of volcanic activity, but there's plenty of them over there. But mostly earthquakes. And bad ones at that. So. We do have some Caribbean activity. You see there's a tiny little plate over here in the Caribbean. South Caribbean, but nonetheless. So, many small ones, 7 big ones. And we care about this because it's responsible for earthquakes, volcanoes, most mountains, and the present, past, and future locations of the continents. Basically, 4 chapters out of your book. So, okay, and that's where we stop for now.